So this is Cryptography Lecture 6, and there are two things I want to do today. One is to talk about digital signatures, and one method for generating digital signatures is RSA, and the second topic will be knapsack cryptography, knapsack encryption. So there are two issues in generating secure communications. So one is to send a message securely, and the second is to verify a message comes from the claimed sender. So let me just explain the difference between these two things. So on the one hand, you have Alice and Bob, and one wants to send a message to the other. And in a public key crypto system, there is what is public knowledge. Let's say in RSA, for example, you have a number N and a number E, and you take your message. So you have your message, which is the plain text, M, and you convert M to a ciphertext. And what is public knowledge, everyone knows how you convert your message into the ciphertext. So for example, in RSA, you take your message and you let C be equal to M to the power E mod N. So and you transmit C to Alice, and Alice deciphers C. She gets back the message because M is congruent to C to the D mod N, and Alice knows D. D is the secret decrypting key. But everyone knows how to encrypt. So here you are, Alice, and Bob wants to have Alice send $1 million to his Swiss bank account. And he sends her a message that says, send $1 million to my Swiss bank account. Here's the account number. And Alice says to herself, so this message says, transfer $1 million to Switzerland to the bank to this account. But how do I know Bob sent the message? Because anyone, Sam could just as well send a message to Alice saying, I'm Bob, and I want you to send $1 million to this account. Alice doesn't know for sure who sent the message. So she wants the message to know who sent the message, right? To know where to send her $1 million. She needs to know exactly that the message is coming from Bob and not from Sam. So what's required is a signature on the message. Or since everything is digital, a digital signature to enable Alice to know for sure who sent the message. Now, of course, the message can say, I'm Bob, send me $1 million. But anyone can say that. You don't know it's from Bob. There has to be a way to verify who the sender is. So that is the problem of creating digital signatures. And this is considered at least as important, maybe more important, than being able to send a message securely. You have to know who is sending the message. And at the same time that Ravesh, Shamir, and Edelman, the RSA in the name RSA, at the same time that they created their encryption scheme, they also created, by almost the exact same way, a digital signature method. And that is what I'm about to explain. So this is the RSA digital signature method. In the text, this is in chapter 4, which I now uploaded to course materials in Blackboard.
Professor, will this chapter 4 be on the exam or
Yes,
the midterm?
everything up to and including what we do tomorrow.
Okay.
Right? So, and this is on the review sheet, which says anything on the review sheet can be on the exam. So chapter 4 is uploaded to Blackboard, but it really is just a few pages. So it is starts on page 193, and there are a couple of pages that are just talking about the matter. And the RSA scheme is on page 196 and ends on page 198. So there really are just a couple of pages you need to read to understand this. So again, let me restate the problem. There is in a public key crypto system, such as RSA or El Gamal, there's a public key. Everyone can send. For some reason, in this chapter, instead of Alice and Bob, they use the name Samantha and Victor. So everyone can send a message and claim to be Samantha. Because in a public key crypto system, everyone knows how to encrypt. It's only the person getting the message who has the secret key that enables her to decrypt. So anyone can send Samantha a message and say, Samantha, send me $1 million. Here's my bank account. But Samantha has to know who's sending it. So there has to be a way when you send a message to Samantha, she can be sure it's coming from the person who claims to be sending it. So in this case, we have two people, Samantha and Victor. And Samantha needs to know that when someone claims to be Victor and sends a message, it really is Victor, that Victor can sign his name to the message in a way that Samantha knows who it's coming from. So just as in the RSA crypto system, in the RSA digital signature system, Samantha chooses two primes, P and Q. She chooses what we'll call the verification exponent, E, where the greatest common divisor of E and P minus 1, Q minus 1 is 1. So E is relatively prime to the product P minus 1, Q minus 1. And what Samantha publishes, that means everyone can know it, are the numbers capital N, which is P times Q, and E. She doesn't say what P and Q are, she says what the product of P and Q is. So this is how you, this is the key creation. This is how you create the key for the signature system. So Samantha publishes the numbers N and E. Okay. Then Samantha computes the inverse of E mod P. She computes D such that D times E is congruent to 1 mod P. So now D is the secret knowledge that Samantha has. And everyone knows N and E. So these are in the public domain. This is Samantha's secret number D. So Samantha's signature, her name, let's just call it S. So it's a number. Everything is converted into a number. And how does Samantha send a document and include with it a verifiable signature, something that only she can send and no one else can send? So Samantha computes she wants to sign a document, Samantha's signature on the document D. So you let S be D to the power D mod N. So Samantha chooses the prime P and Q. She doesn't tell anyone what they are, but she multiplies them to get the number N that she publishes. And since she knows P and Q, she can compute P minus 1 times Q minus 1 and pick an exponent, a number E, which is relatively prime to P minus 1 and Q minus 1, and she publishes N and E. Because she knows, it should be N, because she knows P and Q, she knows N, she can compute a number, she computes D such that D times E is congruent to 1 modulo P minus 1, Q minus 1. She knows P and Q, so she knows P minus 1 and Q minus 1. She can solve this linear congruence. This is all an easy computation. So she knows the number D, and that's her secret. So she takes so she has a document D, and she wants it signed. And the way she signs it is she raises capital D, the document, to the power D mod n. And she transmits this number S. Now, how does she get S? She gets S by raising the document she wants to sign to the power D mod capital N. And she transmits this S. Now, everyone knows N and E. So everyone can take S and raise it to the power E mod N. And S to the power E is D to the D to the power E, or D to the D times E. But DE is 1 mod N. So this is equal to D, which is her signature. So let's say D is Samantha. And that's it. That's it. Let me go through this again, because in some sense, once you know RSA, it's so easy that it seems like you're not doing it. So the problem. How does Samantha sign a document in a way that can be trusted? That cannot be forged. You can't forge her signature. So she wants to send something that says signed by Samantha. So what does Samantha do? She chooses primes P and Q. And because she knows P and Q, she knows P minus 1 and Q minus 1. She can multiply them, and she can choose a number E where the greatest common divisor of E and P minus 1, Q minus 1 is equal to 1. And what Samantha publishes to the world are the numbers N and E. Now, everyone knows N and E. So she wants to send a document which has her name on it. She wants to send her signature. So Samantha computes, she chooses or she computes D such that DE is congruent to 1 mod P minus 1, Q minus 1. If E is relatively prime to this number, it's a unit, it has an inverse. Under multiplication, there's some number D where DE is congruent to 1 mod PQ. And the private key, what is secret, Samantha doesn't tell anyone, is this number D. Now, so Samantha takes her document that she wants to sign, D, and she raises D to the power little d mod n, and this reduced mod n is some number capital S. So Samantha transmits S. Now, S is some number, and if you receive S, so Victor receives S and computes, these are the public numbers, s to the power e mod n. And what is s to the power e? S to the power e is d to the d to the power e. That's d to the de. This is all being computed mod n. D to the de, which is d to the 1 plus some p minus 1 q minus 1 times k mod n. So that's d times d to the p minus 1 q minus 1 k mod n. But d to the p minus 1 q minus 1 mod pq is 1. So this is just d mod n. So Victor sees when he performs this operation, he gets d, which is Samantha's signature. Now, why can't someone else fake a document and send Samantha's signature? Well, whatever is the signature has to have this property, or the code that transmits the signature, S. You recover the name by computing S to the power E. You have to know, yes, you compute S to the power E. Now, in order to get S, you took the real signature, the D, and raised it to the power D. If you don't know little d, you can't compute S. You get little d by solving this congruence. You can't solve this congruence if you don't know the modulus p minus 1, q minus 1, which means you need to know p and q. So you can't encrypt your signature just on the basis of the public knowledge. You need the additional information, the trapdoor, which Samantha has, which are the numbers p and q. And this is the RSA digital signature. Let me do an example to show what it is. So suppose Samantha chooses the primes p equal 541, q equal 1223. And she chooses E to be 159,853. Let's see. So what is going on here? So the public modulus n is p times q. P times q is 541 times 1223. If I multiply them, what do I get? Well, fortunately, I can use Maple. So you can also use a calculator. So let me open up my Maple. So 541 times 1223 is 661,643. And p minus 1, q minus 1 is 540 times 1222. And if I multiply 540 times 1222, I get a little smaller number, 659,000 880. And
Professor, can you please move your paper a little bit up? Can't see it.
sure, just 1 second.
Mm-hmm.
Yeah. So Samantha chooses primes 541 and 1223. If you multiply them, you get 661, 643. P minus 1, Q minus 1 would be 540 times 1222. That's 659, 680. And the number E she picks is 159, 853. And I'm just on my computer here. I'm just double checking that if I take, let's see, no, I want the greatest common divisor of P minus 1, Q minus 1, which is this number 659, 880, and the E, which is 159, 853, that is in fact 1. So the GCD, the greatest common divisor of 159, 853, and 659, 880 is indeed 1. So that's okay. What is the private signing key? So we have to find a number D. So we need a number D such that DE is congruent to 1 modulo P minus 1, Q minus 1. So how do we do this? We have to find a number D such that 159, 853 times D is congruent to 1 mod 659, 880. And let's see. Even with the calculator, this is not so easy to do. So let me see if I can figure out in Maple how to do this. So the only way I know how to do this is to use the Euclidean algorithm. try something else. Just trying to figure out a way to use Maple to do this. Yeah. It doesn't want to. Okay, so I think I figured out how to do it. So I'm trying to solve this congruence. And so I want to solve 159,853 times x is equal to 1 modulo 659,880. Let's see this. So what this says is a solution of this congruence is D equal to 561,517. So you really need a computer to this. I'm using Maple. And let me just check that this is correct. I need to know that the greatest common divisor no. If I take yeah, okay, so this is correct. So if you don't use computers, you can't do much with this, but so, all right. Samantha uses the RSA signature scheme with the primes 541 and 1223, and the public verification exponent 159,853. So I'm just checking that this is all correct. If you take the product of the primes, you get 661, 643. That is the public modulus. She takes E to be 159,853. This has to be a number which is relatively prime to P minus 1, Q minus 1, and I checked on my computer, and it is. So she makes this number E public. So the public information is N equals this, and E equals this. Her private key is the number D, which she gets by solving the congruence DE congruent to 1 mod P minus 1, Q minus 1. That means 159,853 times D is congruent to 1 modulo this. And using Maple, I solved that congruence, and I got this number D. So this is the secret number, the private key that Samantha has. Now, she has a document D she wants to sign. So D, the document she wants to sign, is 635.79. And the signature that she sends is what? So S is D, capital D, raised to the power D, mod N. So that's some humongous number. That's 630,579 raised to the power 561, 517 and you want to reduce that modulo 661, 643. So I don't even know whether Maple is strong enough to do that.
Professor, where did you get the let's say 630,579 from again?
Oh, so this is the document. This is
Mm-hmm.
this number says Samantha.
Oh, so like it's like provided because that's what she's
Right. That's her name.
mm-hmm.
That's her digital name. So
Okay.
so people need to know that the document she sends is signed by the number 63579.
Mm-hmm.
But you can't send that number because anyone could send that number.
Mm-hmm.
And no one who receives it would know that it's really coming from Samantha. So she encrypts this. She encodes this by taking this number and raising it to her secret key D. That
And
means
then
she has
D
to
is
630,579
mm-hmm.
raised to
What we just computed.
561, 517 and reduce it modulo this.
Mm-hmm.
So I want to see whether Maple can do that.
And Professor, I know what's it we're gonna have a little bit more one that we can actually compute for our midterm
Oh,
exam, right?
yeah. Oh, yeah. No. The only numbers on the midterm have to be very, very small. I mean, I assume everyone has at least a calculator and can
Mm-hmm.
do the arithmetic on the calculator. But I'm going to make the numbers as small as possible. Otherwise, it's kind of ridiculous.
Yeah,
So
because
I want to find what happens if I take this number 630,579 and I raise it to the power 561, 517. Modulo 661, 643. And I get that this number is 206, 484. So this is the number that Samantha sends. She sends this number. And if you want to verify that this really is Samantha's signature, you take this number and you raise it to the public exponent e and reduce it mod n. So what I need to do, so to verify, I need to take 206, 484, and raise it to the power 159, 853, and reduce it modulo 661, 643. So let me try to do that. I'm just looking at my computer. So I have 206, 484, raising it to the power 159, 833. And I get the wrong thing. So let me just double check what I've done. And in fact, what I'll try to do is open my Maple worksheet, share screen. Okay. So can you see this Maple worksheet on your screen?
yes.
Yes.
Okay. So let me do all this from the beginning. So Samantha chooses the primes P equal to 541 and Q equal to 1223. And when you choose that number, she multiplies them, and N is going to be P times Q, which is 661, 643. And we have to know what is P minus 1 times Q minus 1. And that number is 659, 880. And she chooses E to be the number 159, 853. Right, so that's E. And it has to be the case, this is just a check, that the greatest common divisor of E and P minus 1, Q minus 1 is 1. So IGCD, which means the integer greatest common divisor of E and P minus 1 times Q minus 1 is 1. Okay, so that's good. And now she needs to find the D such that D times E is congruent to 1 mod P minus 1 Q minus 1. So we want to solve the congruence, the modulus. M-solve means solves this modular equation. The equation is D times E equal 1 modulo P minus 1 times Q minus 1. And that gives me 561, 517, right? So this is what I got before. So this is D. That's the secret key. So now Samantha's signature, the digital document she wants to sign, is given by capital D. I can't use capital D because D means derivative in Maplewood. So I'll just call it X. So X is going to be 630, 579. 630, 579. And that's her actual signature. And she's going to create her digital signature that she transmits. It's going to be X to the, X to the power D, and we want that modulo N. So I want to know what is the remainder when you take X to the D modulo capital N. For this week. Oops. Can't call it D. I'm going to just call it something else. Let's call it Y. And D will be this name. Check if this is good. So D is going to be the number 561, 517. Okay. And this is X. And so X to the D, this is, all right, so that's 206, 484. So that's exactly what I got. And that is S. That's what is transmitted. And so I have to verify that this is really Samantha's signature. So what I do is I take S and raise it to the power D. And I want to reduce it mod n. So I want the integer remainder of S to the D mod n. And that is the wrong answer. Oh, sorry. If I don't want S to the D, I want S to the E. And that is the right answer. Okay, so it worked. So let me just go through this numerically and you see that everything is the way it's supposed to be. So Samantha is sending a message. And people who get the message have to believe, have to know, have to be certain that the message came from Samantha. So she's going to, and she can't just say, this is from me, because anyone could say that. So she has to encode her message in such a way that no one else can encode it. And everyone knows that that's her message. So she chooses P and Q, multiplies them to get N. She finds a number E that's relatively prime to P minus 1, Q minus 1. In that case, that's 159, 853. So what she makes public are the numbers capital N and E. Okay. Then she has to get her private key, which is the inverse of E mod P minus 1, Q minus 1. So she solves this congruence and gets a number D, which is 561, 517. So D times E is congruent to 1 modulo this. So this is her signature. This is what it really is. She wants people to know she's sending it. So she takes her number, her name, X, which is capital D in the text, raises it to the power of little d, and reduces it mod n. This is the number she sends. And she can do it because she knows little d. But no one else knows little d. To get d, you have to solve the congruence, d congruent to 1 modulo this. And if you don't know p and q, you don't know this. But anyone who gets this can raise it to the public power e mod n and see that it's their signature. So that is the RSA digital signature. That's the way it goes. Okay, that's a digital signature. And then in real life, this is used constantly.
So,
It
Professor,
I mean, whatever. Yes.
I'm
In
sorry
real
for
life-
interrupting.
That's right. Let me stop the share. Okay. So what did we get? We got whatever we got.
So, Professor, for
I'm sorry, can
D,
you speak up? I find it hard to hear you.
oh, I'm sorry, Professor, can you hear me now?
Yes.
Okay, Professor, so basically for D, right, what's it for that last question, for D is like the inverse, right, of
E.
what's it, of E, which is 159,853. Okay, I just want to make sure.
Yes.
Okay, I just want to make sure.
Yeah. So I uploaded chapter 4 to Blackboard. Chapter 4 is on digital signatures. It's a very short chapter. And what I just did is one of the problems at the end of the chapter on the RSA digital signature. And All right. So we have RSA, public key to cryptography, and RSA, digital signatures. And these are both based on the difficulty of factoring integers. That is, given P and Q, compute the product N equal PQ, and that's easy. Given N, factor N into a product P times Q is hard. So RSA public key cryptography and RSA digital signatures are both based on the fact that to factor a number is hard. Multiplication is easy, factoring is hard. The El Gamal cryptographic scheme, or let's say the I did this in the order, but I did it. So Diffie-Hellman key exchange and the El Gamal public key cryptography, these are based on the difficulty of computing discrete logarithms. So given a prime P, a primitive root G, and an integer A, computing G to the A mod P is easy. Given G to the A mod P, to compute A is hard. A is the logarithm of, if we call this number B, the logarithm of B to the base G mod P. Computing these logarithms is hard. Exponentiating is easy. Finding a logarithm is hard. So there are two different types of problems we've used so far that in our cryptography. One is factoring, the other is discrete logs. So I want to show one other completely different way to create a secret code. So suppose we have positive integers M1, M2 up to M sub n. And so it's an ordered sequence. And let me give an example. Suppose I have the numbers 2, 3, 4, 9, 14, and 23. So 1, 2, 3, 4, 5, 6 numbers. N is 6. And we have a number S equal to 21, okay, given. And we want to find a subsequence or a subset of these numbers that adds up to 21. So we could have, let's see, 21 is 3 plus 4 plus 14. I could take this sum. Or I have as, say, S is equal to 29. Let's see, 29 is 2 plus 4 plus 23. It's also 2 plus 4 plus 9 plus 14. So there are two different subset sums that add up to 29. Let's see. How can I describe a subset sum for this set? I could take any binary vector x1, x2, x3, x4, x5, x6. So these x sub i's are all 0 or 1. And I could look at the number x1, 2x1 plus 3x2 plus 4x3 plus 9x4 plus 14x5 plus 23x6. So for example, suppose I had my vector 0, 1, 1, 0, 1, 0. That would correspond to the number 2 times 0 plus 3 times 1 plus 4 times 1 plus 0 times 9 plus 14 times 1 plus 0 times 23. That's 3 plus 4 plus 14. That's this 21 that I had started with, right? So taking a subset sum is exactly the same thing as multiplying, almost like what you would call the inner product in linear algebra, of this vector with this binary vector. So there's sort of a one-to-one correspondence between subset sums of a sequence of length n and binary vectors of length n. And so there is what could be called, in general, you have a sequence of positive integers. The subset sum problem is, given a number S, find a subset that sum to S. Or equivalently, find a binary vector x1 up to xn such that summation xi mi, I goes from 1 to n, is equal to S. Now, you can imagine a way to use this to make up a secret code, a cryptographic scheme. So you have your message M, your plain text. Which is, everything is in integers, a number, which you can write in binary. Excuse me 1 second. Okay. So you have this plain text, which is a binary vector, x1, x2, up to xn, and you encrypt by forming the subset sum, summation xi mi, you get some number s. So given any digital vector, it corresponds to a subset sum, a subset of these numbers. You add up those numbers, you get s. And your decryption would be given s, find the subset that adds up to s. And the idea is that sometimes this is hard to do. Sometimes it's hard to do. But you have to make it so that it's always hard to do. So the question is, what's one way to do that? Right? So again, I want to sort of make sure that the basic idea, which we will develop a little bit more, is okay. You have M1 up to Mn. So this is n positive integers. We have x1 up to xn. This is a binary vector. This is our plain text. And from this, we create the subset sum, summation xi m sub I. This is a number s. This is C. This is our ciphertext. This is the plain text. So you send the number s, and whoever gets it has to decipher it somehow by finding out what numbers add up to s. Now, if that's hard to do, the person can't decipher it and doesn't have a code. If it's easy to do, whoever intercepts the message can also decipher it. So it's useless as a code. Right? It's not. Right? So the question is, if someone had a clever idea, how can we modify this scheme and turn this into something that works in cryptography? So the first thing we're going to do is figure out how to create a sequence of numbers where there is an easy algorithm, an easy method to find the subset sum of a number, to invert the subset sum. So we want to find numbers that grow very fast. Let me just give an example. Suppose we take as our sequence 2, 7, 38, 102. Now, these numbers grow fairly fast. And if a number is a subset sum, actually, it's just like, how do you do binary? If you have a number like 829 and you want to write it in binary, you look at the powers of 2, 1, 2, 4, 8, 16, 32, 64, 128, 256, 5, 12, 10, 24. You look for the largest number not bigger than 829, and you pick the largest one. So 829 is 512 plus 317. you pick the largest number that you power of 2, not bigger than 317. That's 256. So this is 512 plus 256 plus 61, I think. What's the largest power of 2 not bigger than 61? Is 32. This is 512 plus 256 plus 32 plus 29. Is 16 plus 13. 13 is 8 plus 4 plus 1. So this is the binary expansion of 829, right? Or this is, if you like, writing 829 as a subset sum of powers of 2. And the algorithm is, when you want to write 829 as a sum of different numbers in this subset, you always pick the largest number you can. And that always works. And the reason why it works is in this sequence, M1, M2, M3, and so forth. In this particular sequence of powers of 2, the I plus first power is exactly twice the previous one. And in general, we want to pick a sequence of numbers. I'll write it as a vector R, R1, R2, R3, up to R sub n. We want to pick a sequence of numbers such that the I plus first number is always at least 2 times the previous number. Okay? And such a sequence is called super increasing. So pick any number you like, positive integer for R1. You let R2 be at least 2 times R1. You let R3 be at least 2 times R2, and so forth. You get the super increasing sequence. And if n is or if S is a subset sum, then S is uniquely determined by, at every step, pick the largest Ri you can and keep going. And that's an algorithm that always works. It always works when you have a super increasing sequence. Now, that makes it easy to decrypt a number. If someone sends you a number and tells you it's a subset sum of a certain subset of a super increasing sequence, you use this method to find the numbers that you need in the sequence that add up to S. But of course, if you can do it, everyone can do it. And if everyone can do it, it's the worst possible secret code, because anyone who intercepts the message can decipher it. So we have to do something to this sequence to make it into a cryptographic scheme. And this was done by Hellman, from Diffie-Hellman, and a colleague named Merkel. This is sometimes called the Merkel-Hellman public key crypto system. And it goes like this. So again, Alice wants to be able to send a message to Bob. So what does Alice do? She chooses a super increasing sequence R1, R2, up to R sub n. So that's some vector of n numbers. Then she chooses 2 numbers A and B, where A is bigger than 2 times the largest number in the sequence, and the GCD of A and B is equal to 1. And then she creates a new sequence, M, M1, M2, up to M sub n, where each of those numbers, M sub I, you get by taking R sub I, multiplying it by A, and reducing it mod B. And then her public key is the sequence M1, M2, up to M sub n. So you start with a super increasing sequence, which is going to be secret. Choose numbers A and B, which are secret. Multiply every term in the super increasing sequence R by A and reduce it mod B. And now you get a sequence of numbers M, which is all jumbled up. It's not super increasing anymore, but you publish this. Now, sorry, this is what Alice is setting up the system. So anyone, Bob is anyone, can send a message to Alice that she can decipher, but no one else can. So Bob has some plain text message X, which is a binary sequence of length n. And Bob then uses M, this public M, so to compute S to be equal to, let's call this X, X times M. That's summation Xi M sub I. I goes from 1 up to n. So Bob makes a subset sum of M, and it's this number S that he sends back to Alice. Now Eve intercepts the message. So E gets S, and she knows S is a subset sum of the M's. And if she knows what numbers are used in that subset sum, she knows this binary sequence X, and she's broken the code. But the problem is, or the point is, M is not super increasing. M is just some jumbled up set of numbers. And to figure out what subset of M gives you the number S is hard. Eve can't do it. I mean, in an infinite amount of time, she can do it, but she doesn't have an infinite amount of time. So Eve can't do it. So Alice gets this message S, gets this number S from Bob. And how does Alice decrypts S? Thus, compute. So Alice knows A and B. Alice computes the number S prime, which is A inverse S mod B. So if S were summation X sub I, M sub I goes from 1 up to n, then S prime is congruent to A inverse S, which is summation X sub I, A inverse M sub I, but M sub I was ARI. This is summation X sub I, A inverse ARI. A times A inverse is 1 mod B. So this is summation xi ri mod v. So Alice gets S prime as a subset sum of the RIs. RI is super increasing. And for a super increasing sequence, there's a very elementary algorithm that gives you the summand. This is the Markov-Hellman public key cryptographic system. And I think I'll wait until tomorrow to do some examples of this. But the interesting thing about this is this uses a completely new idea in arithmetic to create a code. All right, the first codes were used either the difficulty of factoring a number or the difficulty of computing a discrete logarithm. This uses the difficulty of knowing if a number is a subset sum of a set of integers, what is the subset that gives you that subset sum? So it's a completely new idea, which is very, very important. You had a question?
Yes, Professor, because I saw that on the review we're gonna have the super increasing. That's
Yes.
probably gonna be on it, so definitely have to study on that. And what did you say the new cryptography system we're gonna be learning tomorrow is called again?
No, it's not a new one. I said tomorrow I'm just going to explain more about, give some examples of exactly what I did today, the Merkle-Hellman system, and also the RSA digital signature. I'm not going to do anything new tomorrow.
Okay.
But I'm just going to go over these two types of systems in more detail, just to give some examples. But this is as far as the exam covers.
Okay.
Okay, thank you.
And even though the exam is Thursday, the day after tomorrow, in the usual academic calendar, that means there's a week between today and the exam, because every day is a week. But doesn't really help much.
Okay. And Professor, does that mean that we'll just have like will we do like any like, let's say like we get through everything like on like Thursday or something like that, will we like do any of like the review questions, or is just like
Thursday morning, I'm going to be here doing a talk, and I will answer questions and also go through problems on the review sheet. Whatever you have to ask, I'll do.
Okay.
Because the exam's not until 2 o'clock.
Okay, that's great.
So the best thing is, since you're the only two people who show up for these talks while I'm giving them, is to take advantage of that. Work problems on the review sheet so you can ask me the ones you have questions about.
Thank you so much.
Thank you, Professor.
Okay. All right. Bye.
Have a good day. Bye-bye.
Have a great day.